Alpha Centauri is the closest star system to our own. In astronomical terms, it sits almost next door. Its light reaches Earth in just over 4 years, a short journey compared with most stars in the night sky. And yet, despite this closeness, it remains far beyond any human reach. No spacecraft has ever approached it. No signal has ever gone there and returned within a lifetime. It is near in distance, but distant in experience. Welcome to AstraFlow. Here, science drifts like starlight, and curiosity becomes calm. Tonight, let your thoughts slow down, your breathing soften, and your mind settle into quiet understanding. If you're listening from somewhere on Earth right now, you're part of a wide, quiet community doing the same thing. You can share where you're listening from in the comments if you like. And if this kind of slow, science-guided rest helps you, a simple like or subscription gently supports the channel. Now, let's begin and explore the science of Alpha Centauri, secrets of the closest star system. When we talk about Alpha Centauri, we're not talking about a single star. We're talking about a system, a small neighbourhood of stars bound together by gravity. From Earth, 2 of these stars appear as a single point of light, bright and steady. The third is far dimmer, invisible to the unaided eye, yet closer to us than any other star. The entire system lies a little more than 4 light years away. A light year is not a measure of time, but of distance. The spacelight travels in 1 year. Light moves faster than anything else in the universe, yet even at that speed, it takes more than 4 years to cross the gap between Alpha Centauri and Earth. This means that every time we observe the system, we are not seeing it as it is now. We are seeing it as it was more than 4 years ago. If something changed there today, we would not know for years. In astronomy, looking outward is always a form of looking back. Alpha Centauri feels close because our minds are not built to grasp cosmic distances. Compared to stars thousands of light years away, 4 seems small. But for spacecraft, it is enormous. Even the fastest probes humanity has ever launched would need tens of thousands of years to make the journey. So, Alpha Centauri occupies a special place in science. It is the closest example of something still unreachable, a reminder that proximity in space does not mean accessibility. This closeness makes Alpha Centauri important for another reason. If we want to understand how stars like our Sun behave, how planetary systems form, and how common planets might be around nearby stars, this is the first place we look. Not because it is easy, but because it is the most natural comparison. Over the next hours, we will move slowly through this system. We will look at the stars themselves. We will examine how they orbit each other, how their light reaches us, and why some parts of the system are easier to study than others. We will talk about planets that have been detected, signals that appeared and disappeared, and the careful difference between observation and certainty. Nothing here requires imagination or speculation. Everything rests on measurement, patience, and repeated observation. The universe does not reveal itself all at once. It offers small pieces, gathered over time. For now, it is enough to know this. There is a star system closer than any other. It is stable, ordinary, and quietly complex. And tonight, we will take our time getting to know it. When astronomers say that Alpha Centauri is the closest star system to Earth, they're using a very specific kind of distance, not kilometers, not miles, but light years. A light year is the distance light travels in 1 year. Light moves at about 300,000 kilometers every second. That is fast enough to circle Earth more than 7 times in a single second. And yet, even at that speed, light needs more than 4 years to travel from Alpha Centauri to us. This means that Alpha Centauri is about 4 light years away. More precisely, a little over 4. In astronomy, that is extremely close. Most of the stars we see in the night sky are dozens, hundreds, or even thousands of light years away. To put this into perspective, imagine shrinking the entire Milky Way galaxy down to the size of a large city. In that model, our Sun and Alpha Centauri would be living on the same street. They would be neighbours, separated by just a few houses. But even this comparison can be misleading, because while 4 light-years is small on a galactic scale, it is still vast on a human one. If you were to travel to Alpha Centauri at the speed of the fastest spacecraft ever built, the journey would take tens of thousands of years, not generations, civilizations. The idea of distance changes depending on what is moving through it. For light, 4 light-years is manageable. For humans, it is overwhelming. This is why astronomers often describe Alpha Centauri as close, while engineers describe it as unreachable. Both are correct. There is another subtle detail hidden inside this distance. Because light takes time to travel, distance is also delay. Everything we see from Alpha Centauri is already old. When we observe its stars tonight, we are seeing them as they were more than 4 years ago. If a flare erupted on one of those stars this morning, Earth would not know until years had passed. The universe does not send updates in real time. This delay is not unique to Alpha Centauri. It applies to everything beyond our solar system. But because Alpha Centauri is so close, the delay feels almost human-scaled. 4 years is a length of time we can remember. It is the difference between childhood and adolescence, between starting school and finishing it. Astronomy often deals in times far beyond this, millions of years, billions. Compared to those, 4 years feels gentle, and this is part of what makes Alpha Centauri such a compelling object of study. It sits at the boundary between the familiar and the unreachable, close enough that its light feels recent, far enough that no human presence has ever crossed the gap. When scientists point their instruments toward Alpha Centauri, they are not chasing something ancient and distant. They are observing a nearby system that is evolving alongside our own. Its stars are roughly the same age as the Sun. They formed from the same generation of cosmic material. They have been shining for billions of years, just like our star. In a quiet way, Alpha Centauri is part of our local environment. Not our solar system, but our stellar neighbourhood. Understanding this distance helps set expectations. It reminds us why exploration here must begin with observation, not travel, with patience, not urgency. 4 light-years is close enough to matter, and far enough to require humility. Alpha Centauri feels close when we talk about it in light-years. But that sense of closeness changes the moment we think about physical travel. Human technology moves slowly compared to light. Even our fastest spacecraft, designed to escape the pull of the Sun, travel at only a tiny fraction of light speed. At those speeds, reaching Alpha Centauri would not take years. It would take tens of thousands of years. This difference highlights a quiet truth about space. Distance is not just about how far something is. It is about how long it takes to get there using the tools we actually have. On Earth, we're used to closing distances quickly. We cross continents in hours. We send information across the planet almost instantly. These experiences shape our intuition. But space does not follow the same rules of convenience. Between stars, there is no air to push against, no roads to follow, and no shortcuts. Every journey must obey the limits set by physics. Energy, mass, and momentum impose strict boundaries. To reach Alpha Centauri within a human lifetime, a spacecraft would need to travel at a significant fraction of the speed of light. That kind of speed requires energy far beyond what current technology can safely provide. It also introduces new challenges, collisions with interstellar dust, extreme radiation, and the difficulty of slowing down after arrival. So while Alpha Centauri is often described as our nearest neighbour, it remains untouchable in practice. Not because it is hidden or mysterious, but because space itself is vast and resistant to movement. This is an important distinction. Alpha Centauri is not distant in the way ancient galaxies are distant. It is distant in a more personal way, close enough to imagine, too far to reach. This tension has shaped how scientists think about exploration. Rather than planning voyages, they focus on observation. They build instruments that can gather light, measure motion, and detect subtle changes across time. In astronomy, knowledge often arrives without travel. We learn about stars we will never visit. We study planets we will never touch. And yet, this knowledge is precise, reliable, and deeply informative. Alpha Centauri teaches us this lesson clearly. It shows that understanding does not require proximity. It requires patience, careful measurement, and respect for physical limits. Some experimental ideas have been proposed to send tiny probes toward the system using powerful lasers. These ideas remain theoretical. They illustrate how challenging interstellar travel truly is. Even the most optimistic plans involve decades of flight and years of waiting for data to return. So for now, Alpha Centauri remains a destination of thought rather than motion, a system we study from afar, a neighbour we observe through light alone. This does not make it less real. In fact, it makes it more grounded. Everything we know about Alpha Centauri comes from evidence carried across space at a steady, unhurried pace. And that pace sets the rhythm for the rest of our exploration. When we look toward Alpha Centauri from Earth, it appears simple. To the unaided eye, it looks like a single, bright point of light in the southern sky. Even through small telescopes, it can appear as one object. But Alpha Centauri is not one star. It is a system of three. This is an important shift in understanding. In astronomy, a star system can mean one star or many, as long as gravity binds them together. Alpha Centauri is a gravitational family. The two brightest members of the system are called Alpha Centauri A and Alpha Centauri B. They are both similar to our Sun. In fact, they are among the most Sun-like stars known in our local region of the galaxy. These two stars orbit each other in a slow, graceful motion. They are not fixed in place. They circle a shared centre of mass, completing one full orbit roughly every 80 years. From a distance, their light blends together. Only careful observation reveals that there are two sources, not one. The third member of the system is very different. It is called Proxima Centauri. As its name suggests, it is the closest of the three to Earth, yet it is also the faintest. Proxima Centauri is a small, cool star known as a red dwarf. It produces far less light than Alpha Centauri A or B. Because of this, it cannot be seen with the naked eye, even though it is closer to us than any other star beyond the Sun. This creates an interesting contrast. The stars we notice first are not always the ones nearest to us. Brightness and distance are not the same thing. Together, these three stars form a loosely bound system. Alpha Centauri A and B stay close to each other, while Proxima orbits far away, taking hundreds of thousands of years to complete a single circuit around the pair. This arrangement is stable. It has existed for billions of years. Gravity, acting quietly and consistently, keeps the system intact. Understanding that Alpha Centauri is a triple system matters for many reasons. It affects how planets might form. It influences how stars interact with each other over time, and it shapes how astronomers design their observations. Studying a single star is simpler than studying three. Light from one object is easier to isolate. Motion is easier to track. Signals are cleaner. Alpha Centauri challenges that simplicity. Its structure introduces complexity, not chaos but layered motion. Multiple sources of light. Multiple gravitational influences. As we move forward, we will look more closely at each of these stars. We will see how similar some of them are to our Sun, and how different others are. For now, it is enough to remember this. The closest star system is not a single light in the dark. It is a small, balanced system, quietly orbiting itself. The reason Alpha Centauri exists as a system at all is gravity. Not a dramatic force, not a sudden pull, but a steady influence acting over immense spans of time. Gravity is what allows stars to form, to orbit, and to remain bound together. In the case of Alpha Centauri, gravity links 3 separate stars into a single, long-lived structure. Alpha Centauri A and B are the core of this system. They're close enough that their gravitational pull on each other is strong and continuous. Neither star orbits the other directly. Instead, both stars circle a shared point in space known as the centre of mass. This centre of mass is not fixed inside either star. It lies between them, shifting slightly as their positions change. Over the course of about 80 years, the 2 stars complete one full orbit around this invisible point. Their orbit is not perfectly circular. Sometimes the stars move closer together, sometimes they drift farther apart, but the pattern remains stable. The same cycle repeats again and again over billions of years. Proxima Centauri is connected to this system in a much looser way. It lies far from the central pair, thousands of times farther than the distance between Earth and the Sun. Its orbit is slow and enormous, taking hundreds of thousands of years to complete. Despite this distance, gravity still binds Proxima to the system. The pull is weak, but it is enough. Over very long timescales, even small gravitational influences matter. This layered structure, a tight binary pair with a distant companion, is not unusual in the galaxy. Many stars are born in groups. Some remain close. Others drift outward but stay loosely attached. What matters is balance. If gravity were too weak, the stars would separate. If it were too strong, their motions would become unstable. Alpha Centauri sits in a stable configuration. The system has survived stellar evolution, galactic tides, and the slow motion of the Milky Way itself. Nothing about it is temporary. This stability has important consequences. It means that any planets forming within the system have existed in a consistent gravitational environment for a very long time. It also means that astronomers can predict stellar motion with great accuracy. The universe often behaves this way, not through sudden events but through long-term balance. Forces acting gently, continuously, shaping structures that persist far longer than human history. Alpha Centauri is not held together by chance. It is held together by the same physical laws that govern planets, moons, and galaxies everywhere. 3 suns, 1 system, quietly bound. Among the 3 stars in the Alpha Centauri system, Alpha Centauri A feels the most familiar. In many ways, it resembles our own Sun more closely than almost any other nearby star. Alpha Centauri A is a main sequence star. That means it produces energy by fusing hydrogen into helium in its core, the same process that powers the Sun. This stage of stellar life is stable and long-lasting, often continuing for billions of years. In size and mass, Alpha Centauri A is slightly larger than the Sun. It contains a bit more material, and as a result it shines a little more brightly. Its surface temperature is very close to the Sun's, and its colour appears similar, a soft yellow-white light. Because of these similarities, astronomers often describe Alpha Centauri A as a solar-type star. It provides a useful comparison point. By studying it, scientists can test whether what we understand about the Sun applies equally well to other stars of the same kind. This matters because much of astronomy relies on general rules. We study one object carefully and use that knowledge to interpret many others. Having a nearby star that closely resembles the Sun allows those rules to be checked and refined. Alpha Centauri A is also relatively calm. It does not flare as violently as smaller red dwarf stars. Its radiation output is steady on short timescales, creating a predictable environment around it. From the perspective of planetary science, this steadiness is important. A stable star makes it easier for planets to maintain long-term orbits. It also makes it easier for astronomers to detect subtle signals, such as the gentle motion of a star caused by orbiting planets. However, Alpha Centauri A does not exist in isolation. Its close companion, Alpha Centauri b, adds complexity. The gravitational pull between the two stars affects the space around them, shaping where planets could safely form and remain stable. Still, when scientists imagine what a familiar stellar environment looks like beyond our solar system, Alpha Centauri A often comes to mind. It represents something close to home, not identical, but comparable. By understanding Alpha Centauri A, astronomers gain insight not just into this system, but into the broader population of Sun-like stars scattered throughout the Milky Way. A star like ours, shining quietly, only a few light years away. Alpha Centauri b is the second bright star in the system, and at first glance it seems very similar to Alpha Centauri A. Like its companion, it is a main sequence star, producing energy through the steady fusion of hydrogen in its core. But Alpha Centauri b is a little smaller. It contains slightly less mass than the Sun and less than Alpha Centauri A. As a result, it shines with a lower luminosity and appears a bit cooler in colour, leaning toward a softer orange-yellow tone. These differences are subtle, but important. In stellar physics, even small changes in mass can lead to noticeable changes in behaviour. A slightly smaller star burns its fuel more slowly, its internal structure adjusts, its surface temperature shifts. Alpha Centauri b is still very stable, but it is more active than its larger companion. It produces more frequent bursts of high-energy radiation, particularly in the form of X-rays. These emissions come from magnetic activity near the star's surface, where hot plasma twists and reconnects. This activity does not make Alpha Centauri b dangerous or unusual. Many stars of its size behave in similar ways, but it does affect the environment around the star, especially for any planets that might orbit nearby. Because Alpha Centauri A and B orbit each other, their gravitational influence overlaps. Any planet near one star must remain stable despite the pull of the other. This creates regions where orbits are safe and regions where they are not. For Alpha Centauri b, this means that planets would need to stay relatively close to the star to avoid disruption. Farther out, the gravitational influence of Alpha Centauri A becomes too strong. This balance between two stars adds complexity to the system, but it does not eliminate the possibility of planets. It simply narrows the range of stable orbits. From an observational standpoint, Alpha Centauri b presents challenges. Its light blends with that of Alpha Centauri A, making it difficult to isolate. When astronomers search for planets, they must carefully separate the signals from each star. Still, Alpha Centauri b remains a valuable object of study. It offers insight into how stars just slightly smaller than the Sun behave. It helps scientists understand how stellar pairs evolve together over long periods of time. Two stars, similar but not identical, circling each other slowly. A system shaped by small differences and steady motion. Alpha Centauri A and Alpha Centauri b are not fixed points in space. They're in constant motion, locked into a slow orbital dance around each other. This motion is governed by gravity and mass. Because the two stars are similar in size, neither one dominates completely. Instead of one star circling the other, both move around a shared centre of mass. This shared point lies between them, invisible and empty. Yet it determines their paths with precision. The orbit they follow is wide and elongated. At their closest approach, the two stars are separated by a distance similar to that between the Sun and Saturn. At their farthest, the gap grows to more than twice that distance. One full orbit takes about 80 years. That is longer than a human lifetime for many people. Because of this, the motion is subtle. It can only be fully appreciated through long-term observation. For astronomers, this slow movement is both helpful and challenging. It allows the orbit to be calculated with high accuracy. But it also means that changes happen gradually, requiring patience. This orbital motion has important consequences. It shapes the space around both stars. It determines where planets could remain stable over long periods of time. Close to each star, gravity is dominated by that star alone. In these regions, planets can orbit much like they do around the Sun. Farther out, the gravitational influence of the companion star becomes disruptive. This creates natural boundaries. Not walls, but zones where motion is predictable, and zones where it is not. The two stars have likely followed this same pattern for billions of years. Their orbit has survived the slow evolution of the stars themselves. It has endured as they move together through the Milky Way. This kind of binary system is not rare. Many stars in our galaxy are part of pairs or groups. What makes Alpha Centauri special is not the fact that it is a binary system, but that it is the nearest one to us. By studying the orbit of Alpha Centauri A and B, scientists refine their understanding of stellar dynamics. They test gravitational models, they confirm predictions made by physics centuries ago. Nothing about this motion is rushed, nothing is dramatic. Two suns circling slowly, following the same path again and again. In the quiet of space, repetition is stability. Beyond the slow orbit of Alpha Centauri A and B, there is a third star that changes how we define closeness. This star is called Proxima Centauri. Proxima Centauri is the nearest star to the Sun. It is closer than Alpha Centauri A or B, even though it belongs to the same system. The difference is small on a cosmic scale, but enough to give Proxima its name, Proxima, meaning nearest. Despite this, Proxima Centauri is not visible to the naked eye. It is faint, small, and cool compared to the other two stars. If Alpha Centauri A and B are quiet suns, Proxima is more like a dim ember. Proxima Centauri is a red dwarf star. Red dwarfs are the most common type of star in the Milky Way. They are small, long-lived, and burn their fuel very slowly. Because of their size, red dwarfs produce far less light than stars like the Sun. From Earth, Proxima is lost in the background of the night sky, invisible without a telescope. Yet in terms of distance, it is closer to us than any other star beyond our own. Its light reaches Earth slightly faster than light from Alpha Centauri A or B. In this sense, Proxima is our nearest stellar neighbour. Proxima does not orbit close to the other two stars. It lies far away, thousands of times farther than the distance between Earth and the Sun. Its path around the central pair is slow and vast, taking hundreds of thousands of years to complete. This wide separation means that Proxima experiences the Alpha Centauri system differently. It is part of the system, but only loosely bound. Gravity holds it in place, but gently. For astronomers, Proxima Centauri became important not because of its brightness, but because of its proximity. Being close makes small effects easier to detect, tiny motions, subtle changes. This is one reason why planets were first discovered around Proxima rather than around the brighter stars in the system. The star's small size makes the influence of orbiting planets more noticeable. Proxima Centauri reminds us that importance in astronomy does not come from brightness alone. Sometimes the quietest objects tell the clearest stories. The closest star is not the one that shines the brightest in the sky. It is the one whose light reaches us first. To understand Proxima Centauri, it helps to understand red dwarf stars in general. They are small compared to stars like the Sun, often containing only a fraction of the Sun's mass. Because of this, their internal pressures and temperatures are lower. This difference changes how they live their lives. Red dwarfs burn their fuel very slowly. While stars like the Sun will shine for about 10 billion years, red dwarfs can remain stable for hundreds of billions, even trillions of years. They are the longest living stars in the universe. Their light is dimmer and cooler. Most of it is emitted at red and infrared wavelengths, which is why they appear faint to human eyes. From a distance, many red dwarfs are almost invisible, yet they are everywhere. Roughly 3 out of every 4 stars in the Milky Way are red dwarfs. If you could count all the stars in our galaxy, most of them would be small, cool, and quiet. But red dwarfs have another side. Because they are small, their internal magnetic fields can be intense. This leads to frequent stellar flares. sudden releases of energy that send radiation into surrounding space. Compared to the steady output of the Sun, these flares can be abrupt and powerful. For planets orbiting close to a red dwarf, this activity matters. Because red dwarfs are dim, their habitable zones, the regions where temperatures could allow liquid water, lie very close to the star. Planets in these zones receive strong gravitational and magnetic influences. A planet may become tidally locked, showing the same face to the star at all times. One side remains in constant daylight, the other stays in perpetual night. In addition, repeated flares can erode a planet's atmosphere over time. High-energy radiation strips away gases, especially if the planet lacks a strong magnetic field. This does not mean that red dwarf planets cannot exist or cannot be interesting. It simply means their environments are different from Earth's, more extreme, more variable. Proxima Centauri is a typical red dwarf in many of these ways. It flares often, its energy output changes, its planets, if they exist, must adapt to this dynamic environment. Red dwarfs challenge simple ideas about habitability. They remind us that being in the right temperature zone is only part of the story. Understanding red dwarfs helps us understand Proxima, and understanding Proxima helps us understand the most common stars in the galaxy: quiet, small, and numerous. Among the 3 stars in the Alpha Centauri system, Proxima Centauri might seem the least impressive at first. It is smaller than the Sun. It is cooler. It emits only a tiny fraction of the light produced by Alpha Centauri A or B. And yet, Proxima Centauri has become the most studied star in the system. The reason is simple and practical. Because Proxima is small, the effects of orbiting planets are easier to detect. A planet pulling on a small star causes a larger relative motion than the same planet would cause around a larger star. This makes subtle signals clearer. Tiny shifts in position, small changes in light, regular patterns that stand out from background noise. Proxima's closeness to Earth adds another advantage. Because it is nearby, its light reaches our instruments with less loss. Measurements are more precise. Uncertainties are smaller. This combination, small size and close distance, makes Proxima Centauri an ideal laboratory for studying planetary systems around red dwarf stars. It was around Proxima that astronomers first detected a confirmed planet in the Alpha Centauri system. This planet, known as Proxima Centauri b, revealed itself through careful measurement of the star's motion. The star wobbled slightly, pulled by the gravity of something orbiting close by. That discovery did not happen because Proxima was special in a dramatic sense. It happened because Proxima was measurable. In astronomy, importance often follows detectability. The objects we understand best are not always the largest or the brightest. They are the ones that allow careful observation over time. Proxima Centauri also forces scientists to confront the limits of habitability around red dwarfs. It raises questions about radiation, atmospheric loss, and tidal locking. These are questions that apply not just here, but to countless other systems across the galaxy. By studying Proxima, astronomers are not only learning about one nearby star, they are learning about the most common type of stellar environment in the Milky Way. In this way, the smallest star in the Alpha Centauri system carries disproportionate weight. It serves as a test case, a reference point, a quiet guide to understanding a much larger population of stars. Proxima Centauri matters not because it shines brightly, but because it allows us to see clearly. Every observation of Alpha Centauri begins with light. Not light as we experience it on Earth, but light as a messenger travelling through space. When a photon leaves the surface of one of the Alpha Centauri stars, it begins a long journey. It moves at the fastest speed allowed by the laws of physics. Nothing can overtake it. Nothing can shorten its path. Even so, that journey takes more than 4 years. This means that astronomy is never truly about the present. It is always about the recent past. When we observe Alpha Centauri tonight, we are seeing the system as it was years ago. This delay is not a flaw in observation. It is a fundamental feature of the universe. Distance and time are linked. For very distant galaxies, the delay can be billions of years. We see them as they were when the universe was young. For Alpha Centauri, the delay is modest by comparison, but still real. 4 years is a timescale we can understand. It is long enough for change to matter. A star can flare. A planet can complete several orbits. Magnetic activity can rise and fall. Yet none of this reaches us immediately. This has an important implication. When astronomers measure something, a flare, a wobble, a faint signal, they are not witnessing an event. They are receiving information about an event that already happened. Science, in this sense, is always slightly behind reality, but it is reliably behind. The delay is consistent, predictable. Because Alpha Centauri is so close, this time delay feels almost personal. It's not geological or cosmic in scale, it fits within a human memory. When scientists compare measurements taken years apart, they are not just building better data, they are stitching together a timeline of the system's behaviour. Light becomes a record. Each photon carries information about temperature, motion and composition. Collected carefully, these signals allow scientists to reconstruct what is happening far beyond reach. There is something calming about this process. Nothing arrives suddenly. Nothing rushes in. The universe speaks slowly, one photon at a time, and Alpha Centauri, being close, speaks a little louder and a little sooner than most. Alpha Centauri is close in space, but it is not always easy to see from Earth. Whether it appears in the night sky depends on where you're standing on the planet. From the southern hemisphere, Alpha Centauri is a familiar sight. It rises high in the sky and shines brightly, especially during the southern summer months. For observers in places like Australia, South America and Southern Africa, it is one of the most prominent stars in the sky. From the northern hemisphere, the situation is different. Alpha Centauri sits very low on the horizon, or never rises at all. For many observers north of the equator, it remains permanently hidden below the curve of the Earth. This uneven visibility shaped the history of its study. Ancient cultures in the south included Alpha Centauri in navigation and seasonal observation. In the north, it was unknown until global exploration connected different parts of the world. Modern astronomy is not limited by geography in the same way. Telescopes can be built where the sky is darkest and clearest. Space-based instruments observe without atmosphere at all. Even so, Alpha Centauri presents challenges. Because it is bright, it can overwhelm sensitive detectors. Because it lies near the plane of the Milky Way, the background is crowded with distant stars. Separating Alpha Centauri's light from everything else requires careful technique. Astronomers use precise tracking, calibration stars and repeated measurements. They account for Earth's motion, the star's motion, and even tiny distortions caused by Earth's atmosphere. Observation is rarely a single act. It is a process. Images are taken, corrected, compared, and refined. This slow accumulation of data is especially important for nearby stars. Because they move noticeably against the background over time, astronomers must constantly update their measurements. Alpha Centauri shifts its position in the sky year by year. This motion confirms its proximity. Distant stars appear almost fixed. Nearby stars wander. Observing Alpha Centauri from Earth is not about capturing a perfect image. It is about building a consistent record, night after night, year after year. Through patience and repetition, the nearest star system slowly reveals its structure. Everything we know about Alpha Centauri comes from a distance. No probe has ever approached it. No instrument has ever touched its light source directly. And yet, scientists can measure its mass, temperature, composition, and motion with remarkable accuracy. This is possible because stars leave signatures in their light. When starlight is spread out into a spectrum, it reveals patterns. Dark lines appear where specific elements absorb light. Each element leaves a unique fingerprint. By studying these patterns, astronomers can tell what a star is made of. Hydrogen, helium, trace elements heavier than both. Temperature can be measured in a similar way. Hotter stars emit more blue and ultraviolet light. Cooler stars emit more red and infrared. The balance between these colours reveals surface temperature with precision. Mass, which cannot be seen directly, is inferred through motion. When stars orbit each other, their paths reveal how much material they contain. The faster they move, the stronger the gravitational pull must be. In the Alpha Centauri system, the long, well-measured orbit of stars A and B provides an unusually clear calculation of stellar mass. This makes the system a benchmark for testing theories of stellar physics. Distance is measured through a technique called parallax. As Earth moves around the Sun, nearby stars appear to shift slightly against the background of distant stars. This shift is tiny but measurable. The closer the star, the larger the shift. Alpha Centauri shows one of the largest stellar parallaxes ever recorded, confirming its status as our nearest neighbour. None of these measurements rely on a single observation. They depend on repetition, cross-checking, independent confirmation. Errors are expected. Uncertainty is part of the process. Over time, measurements improve as instruments become more sensitive and techniques more refined. This is how astronomy advances, not through sudden leaps, but through careful accumulation. Alpha Centauri is close enough that these methods work especially well. Its motion is clear. Its light is strong. Its position changes measurably over human lifetimes. By studying it, astronomers test the tools they use to understand the entire galaxy. A distant star teaches us about itself. A nearby star teaches us how to measure. Stars carry their history quietly. They do not record it in visible layers or obvious marks. Instead, their age is inferred from how they shine, how they move, and what they are made of. Alpha Centauri is an old system. Not ancient by cosmic standards, but mature. Its stars formed billions of years ago, around the same time as our Sun. This similarity in age is one of the reasons Alpha Centauri attracts so much scientific attention. When two systems form around the same time, comparisons become meaningful. Differences point to physical processes. Similarities confirm shared origins. Astronomers estimate stellar age using several methods. One involves modelling how stars change over time. As stars burn hydrogen in their cores, their brightness and temperature shift slowly. By matching observed properties to theoretical models, scientists can estimate how long a star has been shining. Another method looks at chemical composition. Stars formed later in the universe's history tend to contain more heavy elements, produced by earlier generations of stars. Alpha Centauri's chemical makeup closely matches the Sun's, suggesting a similar formation era. Rotation also provides clues. Younger stars tend to spin faster. As stars age, they lose angular momentum through stellar winds and magnetic interactions. Alpha Centauri's rotation rates are consistent with an advanced, stable age. Taken together, these measurements place Alpha Centauri at roughly 5 to 6 billion years old. That is comparable to the Sun's age. Both systems have had ample time to settle into long-term stability. This matters for planets. Planetary systems need time for orbits to stabilize, time for violent early collisions to subside, time for atmospheres to evolve. A young system is chaotic, a mature one is calmer. Alpha Centauri's age suggests that if planets formed there, they have existed for billions of years. They have experienced long periods of consistent stellar behaviour. Any dramatic early events are long past. This does not guarantee anything about habitability or life, but it does provide a stable backdrop, one where slow processes can unfold without constant disruption. In astronomy, age is context. It tells us not just what a system is like, but how long it has been that way. Alpha Centauri is not a newborn system. It is not in decline. It is settled, steady and quietly enduring. Stars are not made of random material. Their composition reflects the history of the universe up to the moment they formed. Alpha Centauri's stars contain mostly hydrogen and helium, like all stars, but mixed within that simple foundation are small amounts of heavier elements: carbon, oxygen, iron, silicon, and others. In astronomy, anything heavier than helium is called a metal. This term does not mean metal in the everyday sense. It simply refers to elements forged inside earlier generations of stars. The presence of these heavier elements matters. They are the raw material for planets. Stars that formed very early in the universe contain almost no heavy elements. Their planetary systems, if they exist at all, are limited. Stars that formed later inherit enriched material, allowing solid worlds to assemble. Alpha Centauri's chemical composition is remarkably similar to the Sun's. Measurements show that its stars contain roughly the same proportion of heavy elements. This suggests that the environment in which Alpha Centauri formed was not very different from the one that produced our own solar system. This similarity is one reason scientists once expected Alpha Centauri to host planets easily. If the ingredients are present, planet formation is possible. Chemical composition also affects stellar behavior. Elements influence how energy moves through a star. They shape temperature gradients, luminosity, and magnetic activity. By studying Alpha Centauri's spectrum in detail, astronomers refine their understanding of how stars with sun-like chemistry behave over long periods of time. This helps calibrate models used across the galaxy. There is a quiet elegance in this process. From a thin line of light spread across a detector, scientists reconstruct the history of stellar material. They learn which elements are present and in what proportions. No samples are taken, no material is touched. Everything is inferred from light alone. Chemical composition does not tell us whether planets exist. It does not tell us whether life could arise. But it sets the stage. It tells us whether the building blocks are there. And in the case of Alpha Centauri, they are. For most of human history, planets were known only in one place. They belong to the Sun. Other stars are assumed to be distant lights, perhaps with their own worlds, but without evidence. That changed only recently. In the last few decades, astronomers have confirmed that planets are common throughout the galaxy. Thousands have been detected around other stars. These are called exoplanets, planets beyond our solar system. The methods used to find them are indirect. Most planets are far too small and faint to be seen directly. Instead, scientists look for their effects. One method measures tiny shifts in a star's motion. As a planet orbits, its gravity causes the star to wobble slightly. This wobble is small but regular. With precise instruments, it can be detected. Another method watches for dips in starlight. If a planet passes in front of its star, it blocks a small fraction of the light. This creates a repeating pattern that reveals the planet's presence. These techniques work best under certain conditions. Large planets are easier to detect than small ones. Planets close to their stars create stronger signals than distant ones. Because of this, the planets we find first are often not Earth-like. They are massive. They orbit close in. They're easier to notice. This bias matters when thinking about Alpha Centauri. The absence of detected planets does not mean there are no planets. It often means that current methods are not sensitive enough under the conditions present. In a system with multiple stars, detection becomes more difficult. Light from one star interferes with measurements of another. Gravitational interactions add complexity to motion. Alpha Centauri presents all of these challenges at once: bright stars, multiple light sources, subtle signals buried in noise. Still, astronomers continue to search. Not because discovery is guaranteed, but because proximity offers an opportunity no other system provides. Finding planets around Alpha Centauri would not just add another data point, it would give us nearby examples to study in detail, systems close enough that small effects become measurable. The search for exoplanets is not a hunt for certainty. It is a process of gradual refinement. Each observation narrows the possibilities. Around Alpha Centauri, that process is still unfolding. Among all the planets discovered around nearby stars, Proxima Centauri b holds a special place. It was the first confirmed planet found in the Alpha Centauri system, and it orbits the star closest to us. Proxima Centauri b was detected through careful measurement of the star's motion. As the planet orbits, its gravity causes Proxima to shift slightly back and forth. This motion is extremely small, but it repeats with a regular pattern. From this pattern, astronomers inferred the presence of a planet roughly similar in mass to Earth. Proxima Centauri b completes one orbit in just over 11 days. This short period tells us that the planet lies very close to its star. Because Proxima Centauri is dim, being close does not necessarily mean being hot. At this distance, Proxima Centauri b receives an amount of energy comparable to what Earth receives from the Sun. This places it within what scientists call the habitable zone. The term can be misleading. It does not mean the planet is habitable. It simply means that, in theory, temperatures could allow liquid water to exist on the surface under the right conditions. Those conditions are uncertain. Because the planet orbits so close to its star, it is likely tidally locked. One side of the planet always faces the star, receiving constant daylight. The other side remains in permanent darkness. This creates extreme contrasts. The day side may be warm or hot. The night side may be frozen. Whether an atmosphere could distribute heat between these regions is an open question. A thick atmosphere might soften the extremes. A thin one might be stripped away by stellar radiation. And Proxima Centauri is an active star. It produces frequent flares, sending bursts of high-energy radiation outward. Over long periods, this radiation can erode planetary atmospheres. For Proxima Centauri b, this raises serious challenges. Any atmosphere would need protection, possibly from a strong magnetic field. Without it, gases could be lost to space. So Proxima Centauri b sits at an intersection of possibilities. It is close, it is Earth-sized, it lies in a temperature range that attracts attention. At the same time, it faces an environment far harsher than Earth's. The discovery of Proxima Centauri b did not answer the question of habitability. It clarified the question. It showed that planets can exist very close to us, around the most common type of star in the galaxy. And it reminded us that location alone is not enough. Around the nearest star, complexity remains. The phrase habitable zone often sounds more certain than it is. It suggests comfort, balance, maybe even familiarity. In reality, it is a narrow scientific definition with very limited meaning. The habitable zone is simply the region around a star where a planet could, in theory, maintain liquid water on its surface. That is all it describes. It does not account for atmosphere, geology, magnetic fields, or biology. At its core, the idea is about energy. Too close to a star and water would evaporate. Too far away, and it would freeze solid. Between these extremes lies a range where temperatures could allow liquid water to exist. For stars like the Sun, this zone lies at a comfortable distance. Earth sits within it. Mars lies near its outer edge. Venus lies just inside the inner boundary. For red dwarf stars like Proxima Centauri, the situation is very different. Because the star is dim, the habitable zone is much closer in. Planets must orbit tightly to receive enough warmth. This closeness introduces complications. Planets in such orbits are likely tidally locked. They experience strong gravitational forces. They are exposed to stellar activity more directly. So while Proxima Centauri b lies within the habitable zone by energy calculations, that does not make it Earth-like. It simply means that temperature alone does not rule out liquid water. Many other factors matter. Atmosphere plays a major role. A thick atmosphere can trap heat and smooth temperature differences. A thin one offers little protection. Magnetic fields matter as well. They can shield a planet from charged particles and radiation. Without them, atmospheres can slowly be stripped away. Surface conditions also matter. Liquid water requires not just the right temperature, but pressure. If atmospheric pressure is too low, water boils away even at moderate temperatures. The habitable zone, then, is a first filter. It helps astronomers prioritize where to look. It does not predict outcomes. This distinction is important for calm understanding. Science advances by narrowing possibilities, not by making promises. When astronomers say a planet is in the habitable zone, they are not saying it is habitable. They are saying it has not yet been ruled out. Alpha Centauri's planets, known and unknown, remind us of this restraint. The universe offers many environments. Few are simple. The habitable zone is not a destination, it is a starting point. When a planet orbits very close to its star, gravity begins to shape more than just its path. Over long periods of time, it can also shape how the planet rotates. This process is called tidal locking. Tidal locking occurs when one side of a planet always faces its star. The same hemisphere remains in daylight. The opposite side remains in darkness. Earth is not tidally locked to the Sun. We rotate freely, experiencing day and night every 24 hours, but our Moon is tidally locked to Earth. We always see the same lunar face. Around red dwarf stars like Proxima Centauri, tidal locking is common. Because the habitable zone lies so close to the star, planets there experience strong gravitational forces. Over millions of years, these forces slow rotation until it matches the orbital period. For a planet like Proxima Centauri b, this likely means one permanent day side and one permanent night side. The consequences are significant. On the day side, the star never sets. Energy arrives constantly. Temperatures may rise high depending on the atmosphere and surface properties. On the night side, the star never rises. Without sunlight, temperatures can fall sharply. Ice may accumulate, volatiles may freeze out. Between these extremes lies a narrow region called the terminator, the line separating day and night. In some models, this region offers the most moderate conditions, not too hot, not too cold. Whether such balance can exist depends on the planet's atmosphere. A thick atmosphere can transport heat from the day side to the night side through winds and circulation. This can reduce temperature extremes and create a more even climate. A thin atmosphere cannot. Without sufficient atmosphere, the contrast becomes severe. One side scorched, the other frozen. Stellar activity complicates this further. Flares from red dwarfs deliver bursts of radiation directly to the day side of a tidally locked planet. Repeated exposure can strip atmospheric gases and disrupt long-term stability. Tidal locking does not automatically rule out interesting planetary conditions. It simply creates a very different kind of world from Earth. No sunsets, no sunrises, no shifting seasons. Instead, a planet shaped by stillness and contrast. Understanding tidal locking helps us move beyond simple ideas of habitability. It reminds us that planets adapt to their stars in ways that are governed by physics, not preference. Around Alpha Centauri, these processes are not hypothetical, they are expected, and they set the stage for the environments we are trying to understand. Stars are not perfectly steady sources of light. Even calm stars experience periods of activity. For red dwarf stars like Proxima Centauri, this activity can be frequent and intense. A stellar flare is a sudden release of energy from a star's surface. It occurs when magnetic fields twist, build tension, and then reconnect. When they do, energy is released as radiation and charged particles. On the Sun, flares happen occasionally. They can disrupt satellites and radio communication on Earth, but our planet is well protected. Earth's magnetic field and thick atmosphere absorb most of the damage. Red dwarf stars behave differently. Their magnetic fields are often stronger relative to their size. As a result, they flare more often and sometimes more violently. Proxima Centauri is known to produce frequent flares. Some are small, others release bursts of radiation far stronger than anything the Sun produces in the same time span. For planets orbiting close to such a star, this matters. High-energy radiation can heat the upper atmosphere, causing gases to escape into space. Over long periods, this process can thin or completely remove an atmosphere. This effect is cumulative. A single flare may do little. Thousands or millions of flares over billions of years can reshape a planet's environment. A magnetic field can offer protection. It deflects charged particles and reduces atmospheric loss. But not all planets have strong magnetic fields, and maintaining one requires internal heat and motion. For Proxima Centauri b, the balance is uncertain. If it has a strong magnetic field and a dense atmosphere, it might resist erosion. If not, its surface could be exposed to radiation directly. Stellar radiation also affects surface chemistry. Ultraviolet light can break apart molecules. It can alter atmospheric composition and change how energy is absorbed and redistributed. These processes do not make a planet uninteresting, they make it complex. Around red dwarfs, planetary environments are shaped not by gentle sunlight, but by variability. Periods of calm interrupted by bursts of activity. Understanding this helps scientists avoid simple conclusions. A planet's position in the habitable zone is only one factor. Stellar behaviour over long timescales is just as important. Alpha Centauri's smallest star reminds us of this lesson clearly. Energy does not arrive evenly. Stability is something a planet must earn, not something it is given. Being close to a star sounds like an advantage. More light, more warmth, shorter distances. But in stellar systems, proximity often comes with hidden risks. For planets orbiting red dwarf stars like Proxima Centauri, closeness is not optional. Because the star is dim, planets must orbit tightly to receive enough energy to avoid freezing. This places them deep within the star's gravitational and magnetic influence. Gravity strengthens rapidly with proximity. A planet close to its star experiences strong tidal forces. These forces stretch and compress the planet, affecting its rotation, interior, and long-term stability. Over time, tidal forces can slow rotation and lead to tidal locking. They can also generate internal heating, altering geological activity. In some cases, this heat may drive volcanism. In others, it may destabilize the planet's interior. Radiation is another concern. Close-in planets receive a higher dose of high-energy particles during stellar flares. Unlike visible light, this radiation penetrates upper atmospheres and strips particles away. Distance offers dilution. The farther a planet is from its star, the more spread out this energy becomes. Close planets receive concentrated exposure. There is also the issue of stellar wind, a constant stream of charged particles flowing outward from the star. For planets without strong magnetic fields, this wind can erode the atmosphere gradually, molecule by molecule. On Earth, our magnetic field acts as a shield. It deflects most charged particles, guiding them toward the poles and protecting the surface. Without this field, Earth's atmosphere would look very different today. Mars offers an example. It once had a thicker atmosphere and surface water. As its magnetic field weakened, the solar wind stripped much of that atmosphere away. Over time, the planet cooled and dried. Around Proxima Centauri, similar processes may act more strongly and more frequently. A planet like Proxima Centauri b is exposed to these forces constantly. This does not mean such planets cannot exist or persist. It means their environments are shaped by pressure rather than balance, change rather than stability. In astronomy, proximity magnifies influence. What seems like an advantage in energy becomes a challenge in protection. Understanding this helps explain why nearby planets can be both fascinating and fragile. They live close to their stars not because it is ideal, but because it is necessary. Closeness keeps them warm. It also keeps them exposed. While Proxima Centauri has revealed at least one confirmed planet, the search around Alpha Centauri A has been far more difficult. This is not because planets are unlikely to exist there. It is because the conditions for detection are unusually challenging. Alpha Centauri A is bright, very bright. From Earth, it is one of the brightest stars in the night sky. This brightness overwhelms sensitive instruments designed to detect faint signals. When astronomers search for planets, they are often looking for extremely small effects. A slight wobble in a star's motion, a tiny dimming of the light, a faint glow next to a much brighter source. Around Alpha Centauri A, these signals are easily lost. The star's own light floods detectors, masking anything nearby. There is another complication. Alpha Centauri A does not shine alone. Its close companion, Alpha Centauri B, adds a second bright source of light. The two stars move relative to each other, changing their separation over time. This motion makes it harder to isolate one star's signal from the others. Light from Alpha Centauri B can contaminate measurements aimed at Alpha Centauri A. The background becomes crowded and dynamic. In systems with a single star, detection methods are already delicate. In a system with two bright nearby stars, the difficulty increases significantly. Despite this, astronomers continue to search. They use long-term monitoring, advanced data processing, and carefully designed observing strategies. They observe at different wavelengths. They repeat measurements over years. Some tentative signals have appeared and later disappeared. Others remain ambiguous. This is not failure. It is the normal process of refining observation. The absence of confirmed planets around Alpha Centauri A does not mean there are none. It means that if they exist, they are subtle, small, or positioned in ways that current methods struggle to detect. This uncertainty is important to acknowledge. Science does not always provide clear answers quickly. Sometimes it provides boundaries instead. Around Alpha Centauri A, those boundaries are slowly being mapped. Each observation narrows the range of what could be there. The search continues not because success is guaranteed, but because the opportunity is unique. If planets orbit this nearby sun-like star, they would be closer than any others of their kind. And that makes the effort worthwhile. In everyday life, brightness is usually helpful. It makes things easier to see. It brings clarity. In astronomy, extreme brightness can become an obstacle. Alpha Centauri A is so bright that it challenges the very instruments built to study it. Modern telescopes are designed to detect faint signals, distant galaxies, dim planets, subtle variations in light. When a star is too bright, it can overwhelm these sensitive detectors. This creates a paradox. The closer and brighter a star is, the harder it can be to study the faint objects around it. Light from Alpha Centauri. A spreads across a detector, creating glare and diffraction patterns. These patterns are not imperfections in the telescope. They are a natural result of how light behaves when it passes through optical systems. Even when engineers use special techniques to block starlight, a small amount always leaks through. This residual light can hide the signal of a nearby planet that is millions or billions of times fainter. To detect such a planet, astronomers must subtract the star's light with extraordinary precision. They model how the telescope should respond to a bright source. They compare observations of reference stars. They remove patterns piece by piece. This process is slow and careful. A small error can create a false signal or erase a real one. Brightness also limits which instruments can be used. Some detectors saturate when exposed to too much light. Others risk damage. As a result, observing bright stars often requires special modes or indirect methods. Alpha Centauri A sits at the edge of what many telescopes were designed to handle. It is bright enough to strain their capabilities, yet close enough that its planetary environment remains scientifically irresistible. This challenge has driven innovation. Astronomers have developed new techniques to suppress starlight, track motion precisely, and extract information from noisy data. These advances do not benefit Alpha Centauri alone. They improve the study of other nearby stars as well. In this way, Alpha Centauri acts as a testing ground, a place where instruments are pushed to their limits, and where new methods are refined. Brightness, usually an advantage, becomes a lesson in restraint. To see what lies nearby, astronomers must first learn how to look past the light. Alpha Centauri does not exist alone in its search for planets. Its close companion, Alpha Centauri b, adds another layer of complexity. When two stars orbit each other, their light overlaps in subtle ways. From Earth, the separation between Alpha Centauri A and B changes slowly over time as they move along their orbit. Sometimes they appear farther apart, sometimes closer. This changing distance matters for observation. Light from one star can spill into measurements of the other. Even when astronomers aim their instruments carefully, a small amount of unwanted light can enter the data. This contamination is difficult to remove completely. The effect is not dramatic. It does not overwhelm observations outright. Instead, it introduces uncertainty, small variations that must be accounted for during analysis. Planet detection relies on precision. Signals are often buried deep within noise. A slight change in background light can mimic the effect of a planet or hide it entirely. In a binary system, gravity also plays a role. The motion of each star affects the other. This motion must be modelled accurately before any additional wobble caused by planets can be identified. Astronomers must first subtract the known motion of Alpha Centauri A and B around their shared centre of mass. Only then can they look for smaller secondary motions that might indicate planets. This process requires long-term data. Years of observation are often needed to separate stable orbital patterns from temporary fluctuations. The presence of two stars also affects where planets could exist. In some regions, gravitational forces from the companion star would destabilize planetary orbits. In others, orbits could remain steady for billions of years. This limits the zones where planets can safely form and persist. Detection efforts focus on these regions, narrowing the search. Binary stars are common throughout the galaxy. Understanding how to study them is essential for a complete picture of planetary systems. Alpha Centauri offers a nearby example where these challenges can be examined in detail. It allows astronomers to refine techniques that will later be applied to more distant systems. Interference, both optical and gravitational, is not a barrier. It is a condition to be understood. By learning to separate overlapping signals, scientists improve their ability to listen carefully to what the universe is saying. In complex systems, clarity comes from patience. One of the clearest signs that Alpha Centauri is close to us is how much it moves across the sky. Most stars appear fixed, holding their positions night after night, year after year. Alpha Centauri does not. As Earth orbits the Sun, nearby stars appear to shift slightly against the distant background. This effect, called parallax, is subtle, but measurable. For Alpha Centauri, the shift is larger than for almost any other star. This motion is not fast. It unfolds slowly, over months and years, but compared to distant stars, it is unmistakable. In addition to parallax, Alpha Centauri has its own motion through space. The entire system is travelling through the Milky Way, following its own path around the galaxy's centre. This motion causes the system's position to drift steadily relative to more distant stars. For astronomers, this movement is both helpful and demanding. It confirms proximity. But it also complicates observation. When searching for planets, scientists look for tiny, regular shifts in a star's position or velocity. These signals are small compared to the star's overall motion across the sky. Separating them requires careful modelling. First, astronomers must account for Earth's motion around the Sun. Then they must subtract the star's own motion through space. Only after these effects are removed can smaller influences be examined. This process demands precision over long periods of time. Measurements taken years apart must be aligned accurately. Even small errors can accumulate. Alpha Centauri's motion is predictable. Its path through space follows well-understood laws of gravity. This predictability allows astronomers to build detailed models and test them against observation. The system's movement also reminds us that stars are not static landmarks. They are travellers, moving quietly through the galaxy. Over tens of thousands of years, Alpha Centauri's position in the sky will change noticeably. In tens of thousands more, it will drift farther away. Right now, it happens to be near us. Not permanently, just temporarily on cosmic timescales. This sense of motion adds context to our observations. We're studying Alpha Centauri during a brief window when it is close enough to measure in detail. The sky feels still, but nothing in it truly is. In astronomy, not every signal becomes a discovery. Some appear briefly, attract attention, and then fade away when new data arrives. This is not unusual. It is part of how careful science works. When astronomers search for planets around stars like Alpha Centauri, they're working at the edge of detectability. The signals they look for are extremely small. A slight shift in a star's motion, a faint, repeating pattern buried in noise. Sometimes a pattern emerges that looks promising. It repeats for a while. It matches what a planet might produce. But science does not stop there. As more data is collected, the signal must persist. It must remain consistent across different instruments, different observing seasons, and different methods of analysis. If it does not, confidence fades. Around Alpha Centauri, several tentative signals have appeared over the years. Some suggested the presence of planets around Alpha Centauri A or B. Later, with improved models and longer data sets, these signals were explained in other ways. In some cases, the signal came from stellar activity. Stars are not perfectly smooth or quiet. Their surfaces change. Magnetic regions rotate in and out of view. These variations can mimic the effects of an orbiting planet. In other cases, the signal arose from data processing itself. Small assumptions in analysis can amplify patterns that are not physically real. When those assumptions are corrected, the signal disappears. This is not failure. It is refinement. Astronomy advances by learning what not to trust as much as by confirming what is real. Each disappearing signal teaches researchers how to improve their methods. This careful approach is especially important for nearby stars. Because Alpha Centauri is so close, its signals are strong, but so are the complications. Brightness, motion, and multiple stars all interact in subtle ways. A genuine planetary signal must survive all of this complexity. It must remain visible after every known effect is removed. This is why astronomers speak cautiously. They describe candidates, signals, and hints, rather than making immediate claims. Patience protects accuracy. Over time, real signals persist, false ones dissolve. Around Alpha Centauri, the process continues quietly. Data accumulates, models improve, confidence grows slowly. In the calm pace of science, disappearance is not disappointment, it is clarity. In astronomy, seeing something once is not enough. Detection and confirmation are not the same thing. A detection is an observation that suggests the presence of something. It may appear as a pattern, a shift, or a signal that stands out from the background. At this stage, the explanation is still open. Confirmation requires repetition. The same signal must appear again and again under different conditions, using different instruments, and often through different methods. Only then does confidence grow. This distinction matters greatly in the search for planets around Alpha Centauri. Because the system is nearby and complex, many effects can create planet-like signals. stellar activity, instrumental noise, interactions between multiple stars. Even Earth's own motion can introduce patterns. A single dataset cannot separate all of these possibilities. Time is essential. When astronomers collect data over years, they begin to see which signals persist and which fade. True planetary signals follow predictable orbits. They repeat with precise timing. They do not drift or vanish when analysis methods improve. False signals behave differently. They change shape. They weaken. They disappear entirely. This is why scientific announcements are cautious. A planet is not considered confirmed until uncertainty has been reduced to a very low level. Often, multiple research teams must reach the same conclusion independently. Around Alpha Centauri, this caution is especially important. Any claimed discovery would immediately attract intense scrutiny, simply because of the system's proximity. Extraordinary attention demands extraordinary care. Confirmation is not about skepticism for its own sake. It is about reliability. Once a discovery is confirmed, it becomes a stable part of scientific knowledge. It can be used, built upon, and trusted. This process takes time, sometimes years, sometimes decades. But there is a quiet strength in this slowness. Science does not rush to be first, it aims to be correct. In the case of Alpha Centauri, patience ensures that what remains is real, not a momentary pattern, not a hopeful interpretation, just a clear signal, grounded in evidence. Modern telescopes are extraordinary instruments. They can measure tiny changes in light, track motion across vast distances, and detect planets around stars hundreds of light years away. Even so, they have limits. Every telescope is constrained by physics. There is a smallest signal it can reliably detect, and a brightest source it can safely observe. Between these limits lies a narrow window where measurements are possible. Alpha Centauri sits near the edges of that window. Its stars are close and bright. That brightness strains detectors designed to see faint objects. At the same time, the planets astronomers hope to find are small and dim, producing signals that are barely distinguishable from noise. Resolution is another constraint. To separate a planet from its star, a telescope must distinguish two objects that are extremely close together in the sky. At the distance of Alpha Centauri, even planets orbiting at Earth-like distances appear almost on top of their stars. Atmospheric distortion adds another layer. For ground-based telescopes, Earth's atmosphere blurs incoming light. Adaptive optics can correct some of this distortion, but not all of it. Space-based telescopes avoid atmospheric effects, but they face other limitations. They have finite mirror sizes, limited observing time, and strict operational constraints. They cannot focus indefinitely on one target. Technology improves steadily, but slowly. New instruments take years or decades to design, build, and deploy. Each generation offers incremental gains rather than dramatic leaps. This means that some questions about Alpha Centauri cannot yet be answered, not because the answers are hidden, but because the tools are not ready. Astronomers work within these boundaries. They design observations carefully. They choose targets strategically. They accept uncertainty where precision is not yet possible. Limits are not failures. They define what comes next. By understanding what current telescopes cannot do, scientists clarify what future instruments must achieve. Sharper resolution, better light suppression, longer, more stable observations. Alpha Centauri helps guide this progress. Its challenges reveal where improvement matters most. For now, some details remain just beyond reach, not forever. Just for this moment in technological time. Despite decades of observation, Alpha Centauri still holds many unanswered questions. This is not unusual. In science, proximity does not guarantee completeness. We know the system's basic structure. We know the masses of its stars, their orbits, their ages, and their general behavior. But when it comes to smaller details, especially planets, uncertainty remains. Around Alpha Centauri A and B, we do not yet know whether Earth-sized planets exist. We do not know how many planets might orbit there, or at what distances. We do not know whether any of those orbits have remained stable over billions of years. Even around Proxima Centauri, where at least one planet has been confirmed, questions persist. We do not know the planet's atmosphere, if it has one at all. We do not know its surface conditions. We do not know whether it has a magnetic field strong enough to offer protection. Some of these questions may remain unanswered for a long time, not because they are unimportant, but because they are difficult. Astronomy often advances unevenly. Certain properties become well understood early. Others resist measurement and require new tools or new approaches. Alpha Centauri teaches patience. It reminds us that even the nearest systems are complex. They do not yield all their information at once. Uncertainty is not empty space. It is structured, bounded by what we already know. When astronomers say, "we don't know," they usually mean we know the limits of our knowledge. That distinction matters. It tells us where to look next, what kind of instruments are needed, which measurements would be most valuable. In the calm rhythm of science, unanswered questions are not gaps to be rushed across. They are markers of progress. Alpha Centauri remains close, it remains observable, and it remains, in important ways, unresolved. For now, that is enough. Alpha Centauri feels special because it is close, but in the broader structure of the Milky Way, it is not unique. It is one of many stars moving together through a shared galactic environment. Our Sun and Alpha Centauri are part of the same spiral galaxy, orbiting the centre of the Milky Way at roughly the same distance. They are not bound to each other. They are neighbours only temporarily, passing through the galaxy on similar paths. In our local region of space, there are dozens of stars within 10 light-years of the Sun. Most of them are red dwarfs, faint and difficult to see without instruments. Alpha Centauri stands out mainly because it includes stars similar to the Sun and lies slightly closer than the rest. This local grouping is sometimes called the solar neighbourhood. It is not a cluster or a structure held together by gravity. It is simply a region where stars happen to be relatively near one another at this moment in time. Over millions of years, this neighbourhood changes. Stars drift apart. New ones move closer. Distances that feel permanent on human timescales are temporary on galactic ones. Alpha Centauri's current closeness is part of this slow motion. In the past, other stars were nearer. In the future, different stars will take its place. Understanding Alpha Centauri as part of a larger pattern helps ground our expectations. It is not a singular destination. It is an example. By studying it, astronomers learn how nearby stellar systems behave in general. They refine techniques that apply to many stars, not just one. This broader view also softens the sense of isolation. The Sun is not alone in a vast emptiness. It shares its region with many other stars, each following its own quiet trajectory. Alpha Centauri is simply the one we notice most clearly right now. Stars may look fixed in the night sky, but they are always moving. Their motion is slow, measured over long spans of time, yet it is constant. Alpha Centauri is no exception. It is not anchored near the Sun. It is passing by, following its own path through the Milky Way. Our Sun and Alpha Centauri orbit the centre of the galaxy independently. They travel at different speeds and along slightly different trajectories. Right now, those paths happen to bring them relatively close together. This closeness is temporary. Over tens of thousands of years, Alpha Centauri's distance from the Sun will change. It will drift slightly nearer, then gradually farther away. On cosmic timescales, even the nearest star is only a passing neighbour. This motion does not disrupt the system itself. Alpha Centauri's stars remain bound to one another by gravity. They move together as a unit, carrying their planets, dust, and long history with them. The galaxy is full of such motion. Stars weave past each other like slow-moving currents in a vast ocean. encounters are usually gentle, collisions are extraordinarily rare. This drifting shapes the long-term environment of planetary systems. The radiation background changes, the gravitational influences of nearby stars shift. Over millions of years, these small effects can accumulate. For Alpha Centauri, its current position offers us a rare opportunity. It is close enough to observe in detail, yet far enough to remain a separate system. In the future, another star will take its place as our nearest neighbour. Alpha Centauri will recede, becoming just one more point of light among many. Nothing about this process is abrupt. There are no sudden departures, only gradual change. The night sky feels constant because human lifetimes are short, but the stars are always on the move. Understanding this motion reminds us that proximity in space is fleeting. What matters is not permanence, but timing. Right now, Alpha Centauri is near, and for this brief moment we're able to study it closely. When we think about Alpha Centauri, it is easy to imagine it as something static, a fixed neighbour shining quietly in the dark. But every aspect of the system unfolds on timescales far longer than a human life. The stars themselves change slowly. Over millions of years, their brightness shifts almost imperceptibly. Over billions of years, their internal fuel is gradually transformed. The orbits within the system move at a pace that feels gentle and unhurried. Alpha Centauri A and B take about 80 years to complete a single orbit around each other. Proxima Centauri takes hundreds of thousands of years to circle the central pair. These periods are long enough that no single observer can witness a full cycle. Instead, knowledge is built collectively, passed from one generation of scientists to the next. Planetary processes are slower still. Atmospheres evolve over millions of years. Surfaces are reshaped by gradual erosion, impacts and internal activity. If life were to arise, it would do so on timescales that dwarf human history. Astronomy requires comfort with this slowness. Observations rarely offer immediate resolution. Patterns emerge only after years of careful measurement. This is especially true for nearby systems like Alpha Centauri. Because changes are subtle, they must be tracked patiently. Small shifts in motion or light accumulate into understanding only over time. There is something calming about these extended scales. They place human urgency into perspective. They remind us that the universe is not rushed. Alpha Centauri does not demand attention. It continues shining whether or not we observe it. Its stars burn steadily, indifferent to human schedules. In this sense, studying such a system is an exercise in alignment. Science adapts its pace to match the universe, not the other way around. As you listen, there is no need to hold on to every detail. The ideas are meant to settle slowly, just as the processes they describe unfold slowly. Stars change, systems evolve, but they do so in their own time, and that time is vast. Human curiosity often begins with what feels close. Nearby objects seem more reachable, more relevant, even when they remain far beyond our grasp. Alpha Centauri holds this kind of attention. It is not the largest star system, it is not the most unusual, but it is near enough that it feels connected to us. This sense of connection shapes scientific priorities. When astronomers decide where to focus limited observing time, nearby stars rise naturally to the top of the list. Their light is stronger, their signals are clearer, their details are easier to resolve. There is also a practical reason. If we want to understand stars like the Sun, it helps to study examples that are both similar and close. Alpha Centauri A and B offer that opportunity. They allow scientists to test theories developed from studying our own star. Beyond practicality, there is something psychological at work. Nearby stars feel like neighbours, even though the distance is immense. They give structure to an otherwise overwhelming universe. Instead of an endless field of distant points, we begin to recognise a local environment, a region of space that feels familiar through repeated observation. This does not mean Alpha Centauri is destined for exploration or contact. It simply means it becomes a reference point, a way to anchor our understanding. When astronomers talk about planetary systems, habitability, or stellar evolution, Alpha Centauri often serves as a comparison. It grounds abstract ideas in a specific place. This focus is not about hope or expectation, it is about clarity. Nearby stars allow us to test what we think we know. They expose flaws in models. They reveal where assumptions break down. In that sense, caring about Alpha Centauri is not about reaching it. It is about learning from it. The universe offers countless examples. We begin with the ones we can observe most clearly. Long before interstellar travel became a technical discussion, it was a conceptual one. People wondered which stars might be reached first, not in practice, but in imagination. Alpha Centauri naturally filled that role. Because it is the closest star system, it became the first destination people thought about when considering travel beyond the solar system. Not because it was easy, but because it was the least impossible. This pattern appears often in science. When faced with an overwhelming scale, we start with the nearest example. It gives structure to ideas that would otherwise feel abstract. Alpha Centauri serves that purpose in interstellar thinking. It defines a minimum challenge. If reaching another star is ever possible, this would likely be the first. Scientists and engineers have explored this idea carefully. They calculate energy requirements, they model travel times, they test assumptions against the limits of physics. Most conclusions are sobering. Even optimistic concepts involve journeys lasting decades or centuries. Communication delays stretch for years. Any mission would require extreme reliability and autonomy. These exercises are not plans in the usual sense. They are boundary tests. They reveal what physics allows and what it forbids. Alpha Centauri's role here is not to promise travel, but to anchor these discussions in reality. It keeps speculation grounded. When people imagine interstellar probes, Alpha Centauri often becomes the reference distance. 4 light-years is used as a benchmark. Speeds, energies, and risks are measured against it. This kind of thinking has value even without immediate application. It clarifies how vast the gap between stars truly is. It reminds us that exploration is constrained by physical law, not desire. In this way, Alpha Centauri functions as a mental horizon, a nearby boundary that defines what is currently beyond reach. Thinking about it does not bring it closer, but it sharpens our understanding of where we stand. Astronomy advances at a measured pace. Discoveries often come not from sudden breakthroughs, but from years of careful observation and gradual refinement. Alpha Centauri is a clear example of this rhythm. Because the system is close, astronomers can observe it repeatedly, across many seasons and with many instruments. Each observation adds a small piece to a larger picture. No single night provides a complete answer. This process requires patience. Signals must be checked and rechecked. Models must be tested against new data. Early conclusions are often revised as understanding improves. In the search for planets, this patience is essential. A real planetary signal must persist over time. It must appear again after months, years, or even decades. Only then can it be trusted. Slow science is not inefficient science. It is careful science. By moving slowly, astronomers avoid false certainty. They learn which effects come from stars themselves, and which come from orbiting planets. They separate long-term patterns from short-term variation. Alpha Centauri rewards this approach. Its motion is predictable. Its stars behave in stable, measurable ways. Over time, this stability allows increasingly precise understanding. There is also a human dimension to this pace. Many studies of Alpha Centauri span careers. Data collected by one generation of astronomers is refined by the next. Knowledge becomes cumulative rather than immediate. This mirrors the nature of the system itself. Alpha Centauri evolves slowly. Its stars burn steadily. Its orbits change only over long intervals. Science adapts to match that pace. As you listen, there is no need to anticipate conclusions. Understanding is built gradually, just as these observations are. In astronomy, patience is not a delay, it is the method. After moving through the details of Alpha Centauri, it helps to return to the idea that started this exploration, the idea of closeness. Alpha Centauri is the closest star system to the Sun, but the closeness is not simple. It is not closeness in the everyday sense. It is not something we can cross or touch. It is a measured closeness, defined by light travel time, confirmed by careful observation and long-term motion. In science, words often carry precise meanings that differ from intuition. Closest does not mean accessible. It means less distant than everything else of its kind. This distinction matters. It shapes how we think about exploration and expectation. Alpha Centauri is close enough to study in detail, close enough that small motions can be measured, close enough that its light arrives with relatively little delay, but it remains far enough that direct exploration is beyond current capability. This balance defines its role in astronomy. It is not a destination in the usual sense, it is a reference point. By studying the nearest example of a star system beyond our own, astronomers test the limits of their methods. They refine techniques that apply across the galaxy. They learn what can be known from light alone. Returning to this idea also softens the sense of mystery. Alpha Centauri is not hiding secrets in a dramatic way. It is simply complex, governed by ordinary physical laws, 3 stars, gravity, time. Nothing more is required to create a system worth studying for generations. As we come back to the beginning, closeness becomes less about distance and more about understanding. What matters is not how near something is, but how clearly it can be observed. Alpha Centauri offers clarity without immediacy, presence without reach, and that is enough. Alpha Centauri does not announce itself with sudden changes or dramatic events. It does not flare brightly in the night sky or demand attention. It simply remains where it is, shining steadily, moving slowly. In this way, it is a quiet neighbour. Its stars follow predictable paths. Their light arrives at Earth year after year with little variation. Even the activity of Proxima Centauri, though energetic on stellar scales, unfolds within well-understood physical patterns. There is something grounding about this regularity. In a universe that can seem chaotic, systems like Alpha Centauri show how order emerges naturally from basic forces. Gravity keeps the stars bound. Nuclear fusion keeps them shining. Time carries everything forward at a constant pace. Nothing about Alpha Centauri suggests urgency. There is no countdown, no approaching event that requires immediate action. It will remain nearby for thousands of years. It will drift away slowly, almost imperceptibly, over much longer timescales. Its stars will continue burning long after human civilizations change or fade. Seeing Alpha Centauri this way helps set expectations. It is not a mystery waiting to be solved all at once. It is a system to be observed gradually. Science benefits from this kind of steadiness. It allows measurements to accumulate. It lets uncertainty shrink over time. For the listener, this steadiness can be calming. There is nothing to anticipate, nothing to resolve, only a system continuing as it always has. Alpha Centauri remains close, not because it seeks attention, but because it happens to be passing through the same region of space as we are. A quiet neighbour, present, observable, and unhurried. As our exploration of Alpha Centauri slows toward its end, it is natural to notice how much remains unanswered. Not because something is missing, but because knowledge is always incomplete. There are planets we have not yet detected, atmospheres we cannot yet measure, details of stellar behaviour that will only become clear after many more years of observation. Science does not require these gaps to be filled immediately. It allows them to remain open. In astronomy especially, unanswered questions are not failures, they are signposts. They show where understanding ends and where curiosity continues. Alpha Centauri teaches this lesson gently. It is close enough to study, yet complex enough to resist simple conclusions. It reminds us that even familiar systems hold layers of detail. There is no need to resolve everything at once. The universe does not rush. Stars do not change their behavior because we are watching. By allowing uncertainty to remain, science stays honest. It avoids forcing explanations where evidence is incomplete. It leaves room for refinement and revision. This approach mirrors the pace of the system itself. Alpha Centauri evolves slowly. Its stars burn steadily. Its orbits repeat quietly. Understanding grows in the same way. As you listen, there is nothing you need to remember or decide. The information can settle without effort. Curiosity does not need to push forward. Some questions will be answered in time. Others may remain open for generations. Both outcomes are part of the same process. Alpha Centauri remains where it has always been, close in astronomical terms, distant in human ones. 3 stars bound by gravity moving together through the Milky Way, shining steadily, indifferent to observation. We have traced their structure, their motion, and the limits of what we can know, not to reach a conclusion, but to understand the shape of the system as it is. Now, there is nothing left to follow, no new details to track, only the quiet presence of a nearby star system continuing on its path. The universe does not pause, but it does not hurry. As your breathing slows, the ideas can fade gently into the background. Alpha Centauri does not require attention. It will remain, unchanged by our awareness. Knowledge does not need to stay active. It can rest. Everything flows. Sleep in that motion,